Okay, so welcome to our morning session of Monday. Today we have Don Salisbury who will talk about algebraic quantum field theory. Don, go ahead.
Yes. Okay. Thank you so much. I really feel this is a privilege and an honor to be able to address you folks. And I'm so sorry that I was unable to be there in person because I had been looking forward to continuing conversations. So I'm going to talk about field-dependent general covariance and its likely conflict with algebraic quantum field theory. Unfortunately, I'm not going to be able to provide answers to the questions that I will be posing. And in fact, let me go next directly to, how do I change my page? Sorry, there it goes. So just a brief overview of what I intend to talk about. So first introduction, but then I'm going to do some history. In fact, much of this talk is going to be concerned with recent historical investigations that I've carried through and published, beginning actually with Cartan in 1922 and proceeding with Weiss and Schwinger. But then I want to address the Dirac algebra that in fact incorporates this field dependence, which I perceive as a problem. Then I'm going to talk a bit about some recent work I've done in analyzing Peter Bergman's and Art Komar's work on Hamilton-Jacobi approaches to general relativity. And then finally, at the end, I will try to at least pose this question of the conflicts that I perceive arising in this context. Of course, I also welcome any questions or objections along the way, so you should feel free to do so. So what I really intend to do here is to give, as I said, an historical overview and focusing in particular on work that Peter Bergman and his Syracuse group undertook. In this case, mainly in the 1950s, 1960s, early 1970s. In fact, when we get as far as the late 1970s, we get to my own PhD work under Peter's direction, which I completed in Syracuse in 1977. I did want to mention here that Ball actually played an important role in this thesis that I undertook under Peter's direction. I don't recall whether it was Ball or it was Fritz Rohrlich who suggested to Peter that the relativistic string would be an appropriate model to quantize because of its underlying general covariance, or in this case, general reparameterization covariance. And Ball really helped me a lot in preparing to undertake this project. I learned a lot of Virasoro algebra from him, and I'm grateful for that. I do want to say also that I regret that I have not, in the recent past, been following as carefully as I wish I had the work of Ball and so many of his collaborators. It's a really massive collection of important papers. And in fact, I tried to participate in the 316 meeting again recently, and I will try even harder in the future. I've begun to really look more carefully at much of this literature. I wish I had done so in the past. So let me go on to the Cartan formalism. So Cartan's idea was that one could reformulate the laws of classical mechanics, in this case, so with a finite number of variables, by posing this requirement that one begin with a Lagrangian with, can you see it as I move my cursor across the page? Anyone there? Up? Can anyone respond?
No, he can't. Yeah.
Oh, you can't see that?
No, we can't.
Okay, so I'm looking at the variables q and v in the Lagrangian, In the Cartan approach, these were taken to be independent functions of time. And then one constructed a closed interval in the parameter S, such that when one went through the range, S goes from 0 to 1, one actually returned back to the original values of the Q variables and also the B variables. And so Cartan posed this invariant integral request. He said, let's require that this object remain invariant under arbitrary variations of the Q's and the V's, and also the time in this case. So they were all supposed to be parameterized by this parameter S. So he required that this closed interval over S be independent of these variations. And in fact, this immediately delivered the Euler-Lagrange equations. So this was really an important new development, which has since then taken various different important forms. So let me go on here to, of course, the expression, the first in that integral was the usual one form, P dq. That actually was attributed to Poincaré. It's called the Poincaré one form, but then Cartan's idea was to extend this to include the Hamiltonian and increments in the time itself. So this is now called the Poincaré Cartan one form. I want to, in particular, mention here that one thing that Cartan could do very quickly in this formalism was show that one could very quickly derive the Hamilton-Jacobi equations from the use of this invariant integral. So one could require that little p, little dq, and capital P, capital dq, and the corresponding Hamiltonians for whatever model one was considering could be written as the differential of another function, capital G of little q and capital Q. And when one does that, in fact, when one requires that k itself is 0, then one immediately gets to this Hamilton-Jacobi approach, in which case, since the Hamiltonian is 0, one is dealing with constants of the motion, which I'm calling here beta and alpha. And then it's straightforward to show, as I have on this slide, that the result of this change of canonical variables is the usual Hamilton-Jacobi equations. So that the momentum is written as the partial of the action with respect to Q, and then one has the usual Hamilton-Jacobi equation. Of course, one additional wonderful result from this formalism is that then one can set beta equal to a partial of S with respect to these constants, and then from there actually derive the full set of solutions of the classical Euler-Lagrange equations. Okay, so let me go on to Weiss's extension. He actually decided to try to extend the Cartan formalism to field theory, and it's interesting that he was actually a student of Max Born in Germany, but then Born went to England, and in 1936 moved from Cambridge to Edinburgh, and Paul Dirac became Paul Weiss's director. So I think that link is important between Weiss, Dirac, and others, as we shall see. So what Weiss did then was to pioneer this new approach based, in fact, on the Poincaré Cartan increment. He extended it to field theory. And so the idea was, and he did this because he wanted to ensure Lorentz covariance of this formalism. The idea was that he would do this formulation on arbitrary space-like surfaces, which I've indicated here are parameterized by parameter W, which is kind of time-like direction actually, and its 3 parameters U. And then one object which plays an important role in this formalism is the normal, in this case, the covariant normal to whatever surface Weiss chose in which to formulate this extended Cartan principle. So I mention this in particular because, well, first of all, Schwinger himself expressed his own debt to Dirac in his own formulation, his quantum action principle, which indeed was related to Weiss's work. But Dirac never mentioned Weiss, as far as I can tell, in any of his work. Although, but he did refer to Dirac, and Dirac did refer to Weiss in his 1948 important paper on the covariant formulation of quantum electrodynamics. Okay, so Weiss defined a complete variation in which both the fields phi and the space-time coordinates are varied. And then he required, as did Cartan, that these variations lead to new solutions of the dynamical equations, which again we can suppose are labeled by this parameter S, which also in this case could run through a range from 0 to 1, in which case leading back to the original values and leading back, if one wished, to this Cartan invariant integral approach. Now, one important object which appears here, of course, is the increment in the field itself, which I've labeled by phi sub alpha. There are indeed two variations present here, one in the field and the other in the coordinates, in this case, the 4 coordinates, not just the time. And this leads to a variation at fixed space-time coordinates, which is given by this bottom expression for d naught alpha, phi sub alpha. So this is an object which plays an important role in Weiss's formalism, but of course also in the formalism of Dirac. Okay. So then one looks at variations about solutions, and the requirement is that these variations. Yes.
Can you click? There's some boxes appearing in front of your thing. Can you?
So
yeah.
what?
Yeah. Okay. And close that window. Thank you.
Is it okay now?
It's good.
Okay, good. Okay, so I go to the next page. Good. Okay. All right. So so the idea here is that now one wants to require that this increment in the action, provided the equations of motions are satisfied. And I should have pointed out earlier, of course, I'm throughout here, I'm looking at the classical formalism and not the quantum formalism. So one indeed requires that the increment in action should be given by the difference between these three-dimensional integrals over these arbitrary space-like surfaces. So they're labeled by the variables sigma 2 and sigma 1. And I've given you below the definitions of the momenta conjugate to the phis that appear here, and also the momenta that appear conjugate to the x variables. Of course, the naught variable here is in fact just the Hamiltonian in this arbitrary formalism. It is interesting that Peter Bergman also did refer to Weiss's paper in some of his early work dealing with reparameterization, covariant field theory. But Bergman indeed did require the full covariance, the Hamiltonian covariance of his model, and Weiss did not. So the next step here in this history is Schwinger's own action principle, but now, of course, stated in terms of quantum operators. I have noticed that although I think this had not been adequately appreciated in the past, that several of you folks there have referred here to the Cartan-Weiss principle, and I think that's quite appropriate, because I think Weiss did play an important role in the development of Schwinger's own quantum action principle. So I'm simply rewriting here the variations that Schwinger invoked, but of course now in terms of quantum operators. And I don't go through the details of this here, but of course what he was able to show was that ultimately the phi and the pi's turned out to be conjugate variables within this formalism. Okay, so one thing that Weiss did, but Schwinger also did this carefully, was a recommended how to deal with the underlying gauge symmetry in quantum electrodynamics. Schwinger's important step was to assume that the F mu nus and the A's were independent. In fact, it turns out that this was in fact an important lead that was used by Arnoud, Dazer, and Misner in their original treatment of general relativity. But I'm not going to be able to go into that history in detail in this talk, of course. But there is one thing that I want to say here, that even though Schwinger did not make this observation in his original papers, that it does turn out that what he was doing was dealing with an underlying fiber bundle structure, and I think that's something I'm going to give an important role in what follows. So let me go now to Dirac and Bergman, and an individual that you may not be familiar with, T.S. Chang. And I'll explain why I'm doing that here. So I have claimed that Dirac did benefit from Weiss's arbitrary Minkowski space-like surface approach in his 1948 paper dealing with localized quantum systems. And in that paper in 1948, the normal vector does play a decisive role. And also the induced 3 metric appears explicitly in the resulting surface deformation algebra. So in the Dirac formalism. So indeed, in Dirac's formalism, and again, I want to stress this deals with arbitrary space-like surfaces in flat Minkowski space. But he dealt with variations which were perpendicular to the surface and variations which are tangential to it. I think it has not been adequately appreciated that T.S. Chang was certainly engaged in conversations with Dirac. Chang actually got his PhD at Cambridge in the mid-30s. He actually was able to return to Cambridge after the end of World War II. And he was acquainted, of course, very well with Dirac. And when he came back to Cambridge in 1948, or actually it was 1947, Chang actually accompanied Dirac to the Institute for Advanced Study in Princeton. And it is certain that he actually engaged in conversations with Dirac at that stage. I mention this here because it's only recently been discovered, and actually it was pointed out by one of my former collaborators, Yin Xiaodong, that Chang himself had been working on this algebra, which involved the use of this normal to the space-like surface. And in fact, he actually drafted his own paper on this, not being aware that Dirac himself was also writing such a paper. But by this time, Chang was in China, and he didn't learn about Dirac's paper until after he had already written his own draft. But I suspect that Chang was deeply involved. I think also probably because Chang himself had been in contact and was a acquaintance and a conversation partner with Paul Weiss himself. So why is all of this important? Well, it's important in my opinion because Dirac had realized that there was a problem in trying to implement full 4-dimensional diffeomorphism covariance in the Hamiltonian formalism well, in the original case, this was in the formalism of of fields on curved surfaces in flat space-time. But Bergman found, and apparently he was the first to actually have pointed this out, that what Dirac actually accomplished here was something of a miracle because as Bergman pointed out, one looks at the usual Lie algebra of infinitesimal diffeomorphisms in space-time, so in this case in curved space-time, then one arrives at time derivatives of the descriptors of these infinitesimal transformations. And of course, if one looks at commutators of these transformations, then one gets higher and higher time derivatives of these descriptors, and that means that this process is simply not realizable in a phase-space formalism of general relativity, since one has these additional time derivatives that appear. And I think my own view here is that Bergman was the first to have recognized that Dirac had made this important contribution. And Bergman, in fact, was the first to have written down the full variation that resulted from assuming that one deals with field-dependent infinitesimal transformations, which depend on the normal to the space-like surface. And this normal is represented by n super mu. In current terminology, that normal is expressible in terms of the lapse and shift functions in general relativity. And Bergman was the first in 1962 to derive the corresponding algebra. And the crucial observation here is that in this algebra, the inverse to the three-dimensional metric appears within the algebra. Of course, this led everyone to say, well, this is no longer a true commutator algebra because one had this mandatory field dependence. And this mandatory field dependence is, of course, something that I'm placing great stress on, as I have in previous presentations that follows meetings, and I suspect that you're probably, some of you, becoming tired of hearing this story, but I really would like to instigate some conversation on this puzzle, this topic. As far as I can tell, Dirac never wrote down the crucial commutator that applied to the general relativistic case. And as far as I can tell, it was Bryce DeWitt who first wrote this out I think it was in 1967 in a series of papers. And again, we see here that in this commutator of the H naught constraint in Hamiltonian general relativity, it's the 3 metric that appears in this commutator. So what do we do with this is the question. Now, of course, this is not the full story. It turns out, and this is something I've discussed with many of you folks before, it turns out that the full 4-dimensional diffeomorphism covariance is still present in the Hamiltonian formulation of general relativity. But in order to implement it, one has to retain the lapse and shift as canonical variables. And then one is able to derive the full infinitesimal generator of transformations which are written in terms of the normal and attention to the hypersurface. As you see here, the full generator, which I call G script sub psi, is written in terms of primary constraints. The P sub A are, in fact, the primary constraints that result from the absence of time derivatives of the lapse and shift functions. And these C's here are the structure functions that appear in the Poisson brackets amongst these constraints. We actually, one of the first derivations of this full generator, I and my collaborators completed in 1997. course, that derivation was based upon a group theoretical based approach. I'll say a little bit more about this in a moment, but of course, once one has this full generator, then one is able to write down the complete generator for finite diffeomorphisms. And of course, one is still doing this within the classical formalism. The question is, how indeed could one apply this formalism to the quantum theory? Again, I've stressed already that the lapse and the shift have to be retained as canonical variables within this formalism. And I think it's also not adequately appreciated that this classical general relativistic formalism is fully covariant under time new time foliations. Those new foliations involve simply these new multipliers that appear in the full generator. So at least at the classical level, it's possible to retain the full four-dimensional diffeomorphism covariance. But this leads to some problems, and this is the question that I really wanted to address here and hopefully try to instigate a conversation. Bergman himself noted in a 1976 paper, referring to this metric-dependent covariance group. Of course, at that stage, he himself also did not have the full group at his disposal, but nevertheless, he did make, and I'll quote here, make this remark, that these transformations, foremost among them canonical transformations, do not map fiber on fiber or world point on world point. The projective mapping that relates the bundle manifold to the base manifold is lost. Under these circumstances, the fiber bundle becomes unwieldy. And he added later, there is no simple relationship between Dirac's phase space and fiber bundles over the space-time manifold. And interestingly here, he acknowledges conversations that he had held at that time with Andre Trautmann. And I might also point out another article that is worth looking at, short one, called The Fading World Point, which again has to do with this disappearance of the fiber bundle approach in trying to implement this full four-dimensional diffeomorphism covariance. I might also add here, I found this kind of interesting that I had actually given this talk on this full four-dimensional diffeomorphism covariance in Poland with Andre Trautmann. And he did express to me his own concern over the applicability of the fiber bundle approach in light of this metric field dependence that appears in this diffeomorphism symmetry. And you might look, we didn't address this question directly in this paper that we published. This actually is an account of an interview which I did with Andre Trautmann, I think it was in 2016. I think most of you are familiar with the significant role that Trautmann played in promoting fiber bundle approach in general. So let me talk a bit about the Bergman and Komar approach. Let's see, I think I'm going to manage to do this in 35 minutes. I keep time here. So I do want to tell you a little bit about what Bergman and Komar themselves did in relationship to the Hamilton-Jacobi approach to general relativity. I've just recently published an article in the European Physical Journal H, which about this Hamilton-Jacobi history, incorporating actually much of the discussion that I've given you earlier about the roles of Cartan, Weiss, and Schwinger, and ADM, and Kugach. But I'm afraid I can't go into that in detail here. So one thing I do want to mention here, that Bergman very early on strenuously objected to Wheeler's disregard of the full four-dimensional diffeomorphism symmetry. And there was a debate between Bergman and Wheeler on one of the foundation principles of Wheeler's geometric dynamics program. The centerpiece of this program was Wheeler's identification of three geometries. as legitimate observables in his action-based approach. Of course, when I say three geometries here, I do recognize that Wheeler did implement the three-dimensional diffeomorphism symmetries, but not the four-dimensional. In fact, Wheeler and DeWitt and others discounted this full four-dimensional symmetry and replaced it by a notion of multi-fingered time. And I think this is a notion that is dominant still within this field. And I noticed that, at least in some of Val's earlier papers with many of his collaborators, the reference is made to the H naught as implementing time reparameterizations with no mention of the full four-dimensional symmetry that needs to be invoked, I believe, in passing from classical general relativity to quantum gravity.
You have 10 minutes? 10 minutes.
10 minutes? Yeah. Good. I think I'm going to make it. Okay, good. So another thing I thought was interesting here is I think it's not fully appreciated that the role that Bergman himself played in what became known as the Wheeler-DeWitt approach to general relativity. Of course, Wheeler and DeWitt were referring to the Hamilton-Jacobi equation, which results from simply replacing the momenta that appear within the H naught constraint by functional derivatives with respect to the three metric. But I think it's not adequately recognized that it was Bergman who pointed out to Perez that his introduction of this functional came from a Hamilton-Jacobi approach to the gravitational field. Now, just a few words then about what Bergman and Komar did in their own Hamilton-Jacobi approach. First, Bergman was able to show, for a finite dimensional system, that the resulting solution for S could not depend explicitly on the coordinate time. And Komar extended that analysis, in fact, actually attributing it to Bergman, to general relativity, and showing that when one dealt with this system of four so-called Wheeler-DeWitt equations, the resulting S that appears here could not depend on the spatial coordinates. But one thing that Komar did in particular, and I think this is an important development, is he actually decided that in order to fix the three momenta, one needed to add two more Hamilton-Jacobi equations. This effectively amounts to imposing gauge conditions. And then he was able to work out that the solutions of these 6 Hamilton-Jacobi equations could be characterized by diffeomorphism invariants, which I've called here these functions alpha sub a. They are indeed invariant under the full four-dimensional diffeomorphism group. And furthermore, Komar was able to show that there were variables conjugate to these alphas, also invariants. And then in making use of these variables, assuming one was able actually to solve these 6 Hamilton-Jacobi equations, one could in principle obtain the full list of solutions of physically inequivalent solutions of Einstein's equations by setting beta equal to the functional derivative of S with respect to this alpha. So this is work which was done in the late 60s and early 70s. So question is, what happened to space and time here? And I've talked to many of you about this previously, and I just want to briefly mention here that the proposal that I and my collaborators have been pursuing is to fix a gauge by setting the space-time coordinates x super mu equal to appropriate functions of the Weyl scalars. So the x mu then actually become functions of these phase space variables, and that would imply some appropriate approach to quantum gravity that they would become operators. I also want to mention here that I have some collaborators now, actually at Baylor University, who are currently constructing a perturbative mathematical procedure for identifying appropriate candidates for these space-time coordinates. So in nearly flat spacetimes. So unfortunately, I can't report on complete results that we have to date, but the results look promising. I also want to mention here that I did, for Baal's Festschrift, I did expand this Cartan invariant integral approach to Einstein-Yang-Mills theory. And also, I used a new approach to develop the corresponding generator of a mixture of general coordinate invariance with gauge invariance. And I had hoped to be able to make some progress in doing the same thing with the Holst Barbero-Immersi Lagrangian, but I'm afraid that is still an ongoing project. But again, I really look forward to conversations. So apparently, what's the problem here?
5 minutes.
Okay, good. This is very quick here. So I don't see how one can incorporate this field-based approach in the algebraic field theory approach, because in that approach, the smearing variables are presumably space-time coordinates, presumably, or could they possibly be operators? So they could be, I suppose, in the context of the fuzzy physics approach that many of you and Baal have pursued, and I think that'd be something I'd love to talk to you about. But of course, another thing here, and let me just make this final remark here. What about the fiber bundle approach? I simply don't see how many of those theories which have been undertaken by so many of you with so much success, I don't see whether it might be possible to incorporate these field-dependent space-time coordinates into that fiber bundle approach, because as I pointed out earlier, it appears that fiber bundle approach fails when one takes the full four-dimensional diffeomorphism covariance into account. Okay, so that's it. I want to just go through quickly so that people will have an opportunity, if they look at the film here, to see all these references. So I stopped.
Okay. Any questions? Questions? Yeah, I have a question myself. Is there some kind of dimensional reduction to, I don't know, to 1 + 1 dimensions or something like that, where we can work things out more explicitly?
That in principle is a possibility, but is not something which I or my collaborators have attempted. I think it'd be worthwhile investigating those. So okay. I think that would be an exciting exploration to undertake. So I confess here that I've only recently begun to try to look more carefully at the work which many of you have done, and I can see some potential areas in which it might be possible to incorporate some of these ideas within the formalisms that you folks have been undertaking.
Okay. Any other questions? Okay, let's thank Don again.
Thank you so much.
Thank you.